Hello, AP Stat students. In 11.1a, we learned about the chi-squared goodness of fit test. We figured out what the chi-squared statistic was, and then we calculated a chi-squared CDF and compared the p-value to alpha and determined whether we can reject the null hypothesis or fail to reject. In this section, we will continue doing the goodness of fit test, but here in this section, we will do a follow-up. If we reject the null hypothesis, we can perform some follow-up to determine what categories the differences are occurring in. So which category shows the largest deviations from the expected values. So when we did the chi-squared statistic, we would do chi-squared is equal to observed minus expected squared divided by expected plus another one, and so on. Each of these right here is a component. It's an individual calculation. And what it does is it contributes to the chi-squared statistic. The largest contributes the most to the chi-squared statistic. So in our last example, the biggest difference was the groups in the ages 20s and 50s. So in the 20s, the value was 17.49, and in the 50s, it was 14.5175. And so when calculating using lists, the components will be the individual values in list 3. When completing a follow-up, talk about the size and direction of the component from your expected values. So just remember that L3, list 3, is where the chi-squared components are. Let's do an example problem. In his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1st is the cutoff date for youth leagues in Canada, where many NHL players come from, players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if this is true, a random sample of 80 National Hockey League players from the 2009-2010 season was selected, and their birthdays were recorded. Overall, 32 were born in the first quarter of the year, 20 in the second quarter, 16 in the third quarter, and 12 in the fourth quarter. And this was more conveniently done instead of using 12 categories if you did it by month. So instead, it's separated into quarters. In part A, do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year, means not equally distributed? So in the null hypothesis, then there's not going to be a difference. So we will perform a chi-squared goodness of fit test at a 0.05 significance level. And since we're doing quarters, we take the whole probability 1 divided by 4. So each of these is 0.25. For your null hypothesis. And in the alternative hypothesis, at least one of those, P1, P2, P3, P4, is incorrect. And then identifying what the P1, P2, P3, P4 stands for. PI is the proportion of birthdays of NHL players in each quarter of the year, where the 1 for P1 stands for January through March, and then April, May, June, July, August, September, October, November, December. Okay, in our plan, check the conditions, and if the conditions work, we will perform a chi-squared goodness of fit. Okay, it says this is a simple random sample of 80 NHL players from 2009, 2010. Okay. For the large sample, we want to take your P1s, P2s, P3s, and you want to multiply it by our sample size to see what our expected value would be. So we expect 1/4, so 0.25 of 80. That's what we expect, and that is 20. And remember, it has to be greater than or equal to 5. And even though all the values are 0.25, you still have to show it for each one. And so this is for Q1, for Q2, Q3. You can't just say, hey, these all are the same. You have to actually show what you're talking about and what you're doing every step of the way. But they're all 20 and they're all greater than or equal to 5 for each of the quarters. And then for independence, well, we're not sampling with replacement, so it is reasonable to assume that there are more than 800 NHL players in 2009, 2010. Okay, and for our do portion, calculating the chi-squared statistic, remember we must list out at least 2 of the values. So observed, so I'm going to do quarter 1 and quarter 2. So our observed in quarter 1 was 32 were born, minus we expected 20, square it, and then divide by the expected. For quarter 2, it was 20. So 20 minus 20 squared over the expected plus ... And then, of course, the rest you can put in our calculator. So here's what I did. So instead of having to do a separate video, in list 1, I am going to enter my observed. So 32 from quarter 1, 20 from quarter 2, 16 from quarter 3, and 12 from quarter 4. List 2 will be what we get in our large sample. So 20 for each one. That's your expected list. And then L3 would be your L1 minus L2 squared divided by L2. Now remember, we want to put that formula in and it'll calculate it for us so you don't have to do anything by hand. And so here are the components. So 7.2, so that's the contributing to the chi-squared statistic. This one's 0, nice. 0.8, not too far off. 3.2. And when you add all those together, you get 11.2. And then we want to do a chi-squared CDF. So the probability to get a chi-squared statistic greater than 11.2 is equal to lower bound 11.2, upper bound something large. Our degrees of freedom, there are 4 quarters, subtract 1, 3, and that gives us a p-value of 0.0107. Compare that to alpha, and alpha is 0.05, and that's less than. So since our p-value is less than 0.05, we reject the null hypothesis. We do have convincing evidence that at least one of the proportions for people born in each quarter of the year for the NHL is equal. Oh, sorry, is not equal. That should be not. Is not equal throughout the year. Please fix that. Okay, and then we would do a follow-up because we rejected the null hypothesis. So in this case, we concluded that the birthdays of NHL players were not uniformly distributed throughout the year. However, Gladwell's claim wasn't just that the distribution wasn't uniform. He specifically claimed that NHL players are more likely to be born early in the year. Use the values for each component to discuss this claim. So going back to our component, this one contributes, this one contributes. The largest one contributes the most. So you could mention both of them. So I would go about doing something like this. The first quarter has the largest component by having a higher value than expected. And if you look at that first quarter, the observed value was 32, and that's higher than the expected value of 20. And so compare that, make sure you compare that in what direction. The fourth quarter has the second highest, by having a lower value and that lower value 12 than the expected value. This supports Gladwell's claim. And that kind of concludes the chi-squared goodness of fit test. Next time we'll talk about the chi-squared test for homogeneity. Have a great day, AP Stat students.